So, okay. So let me read this to you here. So exchange, we talked about sedimentation. A portion of dissolved CO2 in the ocean combines with calcium ions and makes calcium carbonate. So when I say sedimentation, I want you to think calcium carbonate. So if that's something you think you should write down, I think you probably should. So in sedimentation, it's calcium. So that's where the carbon is held. Calcium carbonate, and it's in sedimentary rocks. Okay, so you have CO2 in the water. You have calcium carbonate due to sedimentation. Then you have some CO2, or some carbon, not CO2, carbon that's buried. So that's called burial. So burial means it's buried underground. It takes forever to decompose because one, bacteria can't get to it, and sometimes it doesn't, it turns into a fossil, right? So that's burial. So you got exchange, sedimentation, burial. Not too difficult to remember what burial means. It literally means what the word means. And then extraction and then combustion. So when we extract it, we extract oil, we extract coal, natural gas. The extraction doesn't affect the carbon cycle. Why? So me just physically taking the coal out of the ground does not affect the carbon cycle.
It doesn't release into the air. It's
right.
solid.
It's still the fossil fuel, right? You haven't burned it yet. So I want to make that clear that us extracting it doesn't affect the carbon cycle until we burn it.
So hydrofracking bad though?
It's terrible for the environment.
Because the gases sometimes just come out and you don't frack them.
So the fracking is to essentially break through to get to the oil or natural gas, and yes, the gas can come out. But that if it's natural gas, so that's CH4. So you're right, that can contribute to it. So you do have a point. So fracking can affect this, but also the chemicals that we use to, I don't know if you understand how it works, but there's chemicals pumped down and essentially like it kind of explodes the rock so that we can get to the gas. But those chemicals get into groundwater. I mean, I don't know if you guys have heard of people lighting their tap water on fire. It's really cool. So it's almost as cool as acid rain. So anyways, yes, Will, you're right. That could happen. But in general, the combustion is the part I'm focusing on. So when we take all of this and start burning it very quickly, it does not keep this in a dynamic equilibrium. It does not keep this in a steady state. Steady state is the key. So I'm just going to write that down. So the carbon cycle without combustion of fossil fuels, carbon cycle without combustion of fossil fuels is in a steady state. Oops. And what that basically means is the CO2 that's being produced and consumed is fairly balanced, right? The negative feedback loop. But again, when we, with combustion, so I'll just say with combustion, the cycle is disrupted. Cycle is disrupted because we are increasing the amount of CO2 going into the air, and it cannot be taken out as fast. So these fossil fuels should take millions and millions of years to maybe decompose eventually if there's erosion and if they're exposed, and so the stuff that's buried, maybe if it was natural processes, would eventually release its CO2 extremely slowly. Instead, we're burning it literally in seconds. Let's see here. So yeah, this is what I wrote. Without humans, the exchange between carbon in the atmosphere and the earth is steady state. The carbon used in photosynthesis is returned to the soil, decomposes, release carbon about as fast as it is added. So that's what that means by steady state. We've kind of talked about this already. But that is what should be happening. But now that we've sped up releasing CO2 at an incredible rate, that is disrupting the steady state, disrupting the balance, the carbon cycle. else do I have here? So as far as carbon dioxide sinks or carbon sinks, it's basically the sedimentary in the file. That's where it's kind of get stuck, think of it that way. It's not being constantly transferred like the surface with the water, volcanoes, respiration, photosynthesis. So that's surface. The stuff that's buried or sedimentary is where the carbon gets held. And one more thing I just want to, let's list in this whole cycle, this picture here, where's one area where the carbon is held just temporarily, very short term. What? The ocean. Good. Where is it held for a long time?
Ground.
Correct. Fossil fuels, sedimentary. I kind of just said it, but I write myself little notes, specific things that the curriculum says you need to know for this. It could be on the test. And specifically, they made a big deal saying, can students look at this? Where are sources of carbon? Where are sinks? Where does the carbon go? And where is the carbon held for short periods of time versus long periods of time, right? So the CO2 in between photosynthesis respiration is fairly quick compared to fossil fuels. The CO2 in the ocean, the exchange, fairly quick compared to sedimentary, all right, in the burial. So just keep that in mind. Good. All right. I want to show you this video. It's 10 minutes. I really want to just move on, but I do think it's worth you guys seeing this here.
Yes, this is home. This is Earth. Having trouble finding a familiar continent? The past is another planet. Actually, many. I'm standing on the great expanse of time that has elapsed since the Big Bang. In order to think about it, we've compressed it all into a single year. It's the early morning of December 23rd on this cosmic calendar of ours, or about 350 million years ago, when our world was a mere 4 billion years old. Earth looks so different, you might not even know the place. The stars wouldn't help you.
Have you guys ever taken a class or talked to anybody or watched anything and understand what he means by a calendar? If you take the entire, from Big Bang to current, and you put it on a calendar, where are we?
We're like the last day of December.
Yeah, even. Keep going.
Last minute.
Yeah, we're like within the last minute of the last minute of that year. That's how old everything is compared to us, which is kind of crazy. I use that in astronomy. That's a way to get kids to understand how old the universe is. It's not perfect, but it helps a little bit. But.
Even the constellations would have been different back then.
Sorry, these tangents, but they're relevant. Why? Why were the constellations different?
Because they're all moving.
Everything's moving. The Earth is moving. The galaxy's moving. So the Earth is rotating and orbiting, but I think I told you this before. It's also wobbling. You know what that means? Yeah, like a top. You spin a top. When a top slows down, it kind of does this. It's called precession. Earth is doing that. So the North Star, for example, won't be the North Star. It's every 26,000 years it goes through a wobble. So what year are we on? Good question. I don't know. We just still, the North Star is still considered a North Star, so I don't know. Just check right now that one. Moving on. I'll let it go.
The dinosaurs were still more than 100 million years in the future. There were no birds, no flowers. The air was different too. The atmosphere had more oxygen than at any other time in Earth's history, before or since. This allowed insects to grow much larger than they do today. Now, insects don't have lungs. Life-giving oxygen is taken in through openings in the outside of their bodies and transported through a network of tubes. If an insect were too large, the outer reaches of these tubes would absorb all the oxygen before it could ever get to its internal organs. But during the Carboniferous period, the atmosphere had almost twice the oxygen as today. Insects could then grow much bigger and still get enough oxygen in their bodies. That's why the dragonflies here are as big as eagles, and the millipedes the size of alligators. So why was there so much oxygen back then? It was produced by a new kind of life.
I think this is his little intro. I'm gonna skip this business. Does anyone know what new kind of life?
Trees.
Trees are kind of a big deal.
What kind of life could have changed the Earth's atmosphere so dramatically? Plants that could reach for the sky. Trees. In their competition for sunlight, trees evolved a way to defy gravity. Before trees, the tallest vegetation was only about waist high. And then, something wonderful happened. A plant molecule evolved that was both strong and flexible, a material that could support a lot of weight, yet bend in the wind without breaking. Lignin made trees possible. Now, life could build upward, and this opened a whole new territory, a three-dimensional matrix for communities far above the ground. Earth became the planet of the trees. But lignin had a downside. It was hard to swallow. When nature's demolition crew, fungi and bacteria, tried to eat anything with lignin in it, they got a really bad case of indigestion. And termites wouldn't evolve for at least another 100 million years. What to do with all those dead trees?
So, this is extremely relevant to the carbon cycle, that's why I'm showing you. So this molecule, when the trees and vegetation started creating this, that's when trees became a thing. Is that a sneeze? Okay, bless you. It's very rigid, and that's essentially what allowed them to keep growing up instead of falling over. They could support themselves. So that's really big deal. But when decomposers and bacteria, fungi try and eat it, it doesn't work too well. So you probably know where that's headed, hopefully. There you go.
It took the fungi and bacteria millions of years to evolve the biochemical means to consume them. Meanwhile, the trees just kept spraying up, dying, falling over, and getting buried by the mud that built up over eons. Eventually, there were hundreds of billions of trees entombed in the earth, buried forests all over the earth. What possible harm could come from that?
This is cool. Real cool.
This cliff in Nova Scotia is another kind of calendar. It tells the story of that other world that once flourished right here. And this is the death mask of that 300-million-year-old tree. It was cast by minerals that replaced the original wood cell by cell. In other words, a fossil. The tree surrendered its organic molecules to the environment long ago. Its carbon and water, only its shape remains. When this tree was alive, it took in carbon dioxide and water and used sunlight to turn them into energy-rich organic matter. The tree gave off oxygen as a waste product. That's what trees and other plants still do. When plants die, they decay, and this reverses the transaction. Their organic matter combines with oxygen and decomposes, putting carbon dioxide back into the air. This balances the books for the chemistry of Earth's atmosphere. But if the trees are buried before they can decay, two things happen. They take the carbon and store its solar energy with them, and leave the oxygen behind to build up in the atmosphere. That's what happened around 300 million years ago. There was an oxygen surplus. That's how the bugs got so big. And what became of all that buried carbon? It lay there for eons before dealing life on Earth. Its most devastating blow of all time.
So he's going to get back to that. We still got a few minutes, but I said this a couple weeks ago, at the very beginning of school, I think. that all the green life on Earth, really the most important thing is absorbing CO2. The amount of oxygen is basically still left over from millions of years ago. It was, like he said, twice, so let's say 40% of the air, but over time, some of it's gone through cycles, and now we're balanced at 20%. But so the excess oxygen was because all those fossil fuels buried were never allowed to decompose and use that oxygen, right? The decomposing bacteria and fungi need that oxygen when they're decomposing. So again, just repeating that, that's important to understand. So that's where the oxygen essentially came from, the surplus, and now we're at 20%.
There are places on this planet where you can walk through time and read the history written on rocks. This beach in Nova Scotia is one of them. Every layer is a page. Each one tells the story of a flood, one after another, over millions of years. The layer cake of flood deposits was slowly buried and turned into rock by heat and pressure. The same forces that built mountains then tilted and uplifted them, along with the entombed fossil forests. The newer layers were always deposited on top of the older ones. All the pages are in the correct order, bearing witness to what happened here over millions of years. Back that way lies the more distant past. With every step I take, I move about 1,000 years closer to the present and away from the world of 300 million years ago. 50 million years later lies that way. This was the beginning of the end of the Permian world, an event of unequaled carnage. The Permian is the darkest corridor in this memorial to the broken branches on the Tree of Life, the halls of extinction. Death has never come so close to reigning supreme on this world in the 250 million years since. The eruptions in what is now Siberia lasted for hundreds of thousands of years. The lava flooded and buried more than 1 million square miles. This event dwarfs any volcanic eruption in historical times. Huge quantities of carbon dioxide came pouring out of volcanic fissures. This greenhouse gas warmed the climate, and this is where the long-buried forest of the earlier Carboniferous period re-entered the story. During the intervening 50 million years, those trees had turned into immense deposits of coal. And as it happened, one of the world's largest accumulations of coal was buried right there in Siberia. The heat from the lava baked the coal, driving methane and sulfur-rich gases out of the ground. They were laden with toxic and radioactive ash particles. Coal smoke. This witch's brew polluted the atmosphere and radically destabilized Earth's climate. A sulfuric acid haze blocked incoming sunlight and darkened the planet. Global temperatures plummeted to sub-freezing. During lulls in the eruption, the acid haze fell back to the surface, but the carbon dioxide remained and built up in the atmosphere to cause global warming. Years of frigid cold alternating with millennia of stifling heat battered a dwindling population of plants and animals. They had no chance to adapt to the drastic swings in climate. As the global warming continued, the surface and the bottom waters slowly mixed, raising the temperature of the once frigid depths of the seafloor. Methane-rich ices that had been frozen in the sediments began to melt. Newly liberated methane gas made its way to the surface and into the atmosphere. Methane traps heat far more efficiently than carbon dioxide, so the climate got even hotter. And the methane also destroyed the ozone layer in the stratosphere. The natural sunscreen that protects life from deadly ultraviolet rays was eaten away. circulatory system of the world ocean shut down. These stagnant waters became oxygen starved, killing almost all the fish in the sea. But one kind of life flourished in this brutal environment. Bacteria that produced deadly hydrogen sulfide gas as a waste product. That was the last straw. The poison gas killed almost all the remaining plants and animals on the land.
This was the Great Dying. The closest life on Earth has ever come to annihilation. 9 in 10 of all species perished. It took a long time for life to develop.
Okay, and so we're going to stop there. So part of the carbon cycle, he explained it there, where the carbon came from, and then it was all released all at once with all the volcanic activity. The buried forest turned to fossils, it was exposed. Then as temperatures fluctuated, because of the haze that blocked the sun, it got cold, but the gases trapped the light when it was able to get through the haze, and the Earth warmed up. The methane, so this is something you need to know. Methane is a greenhouse gas, and it traps heat way better than CO2. So CO2 is a big problem with greenhouse gases. Methane, CH4, is even bigger as far as if you were to compare one molecule to the other. It's just we produce way more CO2 than methane. That's why we focus on that. Does anyone know another greenhouse gas that you may not think of, that you may not think is a greenhouse gas? What? Water vapor is a greenhouse gas. That's another one. Those are the three. Those are the top three: CO2, methane, and water. So, what the irony here? Maybe not irony is the word, but so millions of years ago, when all those fossil fuels were exposed, the volcanic activity and lava baked all the coal, essentially, and created the mess, the sulfur dioxides, the nitrogen oxide compounds, the sulfuric acid, the rain, the methane, the CO2. That's all happening now. We are doing that. It's just we're doing it much slower, but very fast, but much slower than a volcano torching a million acres like fairly quickly. But so there's a lot of things in this just 12 minutes that applies to this class and things you need to know. Greenhouse emissions, what are they? How does that work? Fossils, the carbon cycle, and if you burn them, what happens? So I saw this, I'm like, this is literally perfect. So there's a lot going on in that because you do need to know about air pollution. That's another unit we'll get to, but you know, we're going to sprinkle it in throughout the year. But yeah, so it's pretty fascinating, and the Earth survives, right? The Earth will make it, and that's the scary part is, you know, it's the humans that aren't going to make it if we don't change, but the Earth will make it because it's been through worse times. So anyways, I just thought that was really, really cool video there. All right, let's finish up with these cycles. So stay with me here. I know we're doing a lot of notes here today, but I want to get this unit 1 done. All right, nitrogen cycle. So flip the page. Page 87 is the nitrogen cycle, I believe. So it's movement of nitrogen through the, I think this is the first slide, yeah. Movement of nitrogen through the biosphere. Nitrogen is a macronutrient. There's 6 key elements that an organism needs. You should write those down. Nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. Nitrogen's a big part of that. It's called a limiting, well, it can be a limiting nutrient. A nutrient required for the growth of an organism, but available in lower quantity than other nutrients.
Cheese stick time.
Cheese stick. That's funny. I don't eat those anymore, really, but that's a funny story. Yeah.
Why? Don't tell me they're bad.
No. I don't eat as much dairy as I used to. It's an inflammatory food. But. No. Cheese. As long as it's like normal, natural cheese, then it's good.
All right. I was like feeling good about this. Now I'm like kicked in the
No. It's good. It's good.
Okay. All right. Good.
Eat it. All right. Let's see. Where's most of the nitrogen held in the biosphere? Where do we find it? Air. 80% nitrogen is the air. I think it's like 78 point something. So the air, you need to write that down if you don't know that. The biggest source of nitrogen is the air. How do we use nitrogen, and how do plants use it? plants use it to grow, but what does nitrogen help build? I know you're writing this and listening and doing a lot, so I'll give you a minute here.
So what else is in the air then, besides nitrogen and oxygen?
Those are almost, so that puts us at like 98% or something like that, pretty close to that. CO2 is a certain percentage, so it's not 2% though. And then there's trace gases, like other ones, like radon. There's radon. Trying to think of some other ones. There's just such a small percentage, no one really talks about them, and I don't know them all either. But, you know, methane's in there, right? I mean, depending on where you live, there's a lot of methane in Liz's air, probably. Cows.
Wouldn't there be a lot of nitrogen too?
Yeah. Yeah. No, I'm just joking with you. I mean,
Yeah.
that's what part of the gas they release. All right. So I have 5 parts to the nitrogen cycle. This slide kind of drags it out a little bit here. So, but nitrogen fixation, make sure you write that down. That's the first part of this cycle, and I'll refer to the picture here when we're done with this, with the definitions. Process that converts nitrogen gas into forms of nitrogen producers can use. Oh, I never answered my question. I'm sorry. So how do we use it? How do plants use it?
Use what?
Nitrogen. Why is it vital? What does it do in our body?
Just corrupt.
Yep.
Really?
Yeah. It helps build these things that help build other things.
Amino acids.
Yes. So at some point, somewhere in your notes, make sure you write that down. We use nitrogen to build amino acids, which build proteins. And proteins are a big deal. People think protein and they think muscle, but proteins, there's very small proteins. There's proteins used for almost every process in our body. I'm not an expert, but I know it's used in a lot of processes. So without the amino acids, without the essential amino acids, without protein formation, a lot of functions, a lot of processes in our body will not work properly. What are we made of? What makes us who we are? DNA and RNA. Nucleic acids. Lots of nitrogen involved with those. Without nitrogen, it doesn't work. All right, you guys remember in biology probably talking about this. And again, this is, I know, surface stuff here with this, but you have like your nitrogen, and then you have that matches up with another element. You have the bases, and you got your, what's the U on the DNA? Anyway, you know what I'm saying. I don't want to go. I don't want to talk out of turn here and say something that isn't exactly correct, but nitrogen's a big part of it. So nucleic acids, amino acids, big deal. Okay, do plants have DNA? Yeah. So that's what we have in common there. One thing with the nitrogen. So anyways, you got nitrogen fixation. So we need the nitrogen to get into the ground so producers can use it. So that's a big deal for plants. Nitrification, this is kind of amazing to me. The conversion of ammonia, which is NH3, they have NH4+, which is ammonium. We'll cut them some slack there, but you have ammonia, which will be turned into NH4+, then it's turned into nitrite, and then into nitrate. I'm going to add a little bit to these.
What is that? Like, where does that occur?
Yeah, so that's what I'm going to talk about here. Bacteria do that. Where are bacteria? In the ground. So the nitrates, nitrites, ammonium, those are usable forms because they're water soluble. They get in the water and the plants can absorb it. So the nitrogen gas doesn't get it done. It has to be converted. So the nitrogen fixation is how the nitrogen gas gets put into the ground so producers can use it. Then bacteria convert the ammonia and the NH4 plus into, so essentially it goes N2 gas into the ground into ammonia, NH4 plus, bacteria then convert it into nitrates, nitrites, very soluble, and then it gets in the water and then the plants can absorb that into their tissue. This here, next to nitrogen fixation, I want you to write, it's a special type of bacteria. It's like amazing. Can I spell that right? Yeah. Cyanobacteria. They do not need oxygen to do their thing. Most bacteria do. Cyanobacteria can just straight up take nitrogen and convert it into ammonia and ammonium. So the bacteria, so you have N2 gas, they interact with these special types of bacteria. And this is all they do. That's what they do. They're very specialized. And that turns into NH3, which turns into NH4 plus, and then in the nitrification, the NH4 plus is turned into the nitrite and the nitrate. And if you remember anything about chemistry, the nitrate is really soluble, and that's good. That mixes with the water. And I know I've said that a bunch, but I want you to understand that's why these processes are so important. Without these bacteria, without this fixation, and without the without that process, it wouldn't be able to be absorbed by plants, and we would have no plant life. So those are extremely important organisms. Let's see. Yeah, so I wrote here NO3 minus is better than NO2 minus. And I didn't write why, but from my chemistry part of my brain, it's because I believe NO3 minus is more soluble. All right, assimilation. This is when, so now these ions can be absorbed into the tissue. Next, we have mineralization. So part of the assimilation that isn't on the PowerPoint here that I'll just say, you don't necessarily have to write it, but you know, we breathe in nitrogen gas, obviously, but we get nitrogen from plants we eat as well. That's part of that assimilation. So mineralization, I have organisms die and decompose, fungi and bacteria break down organic matter in dead organisms and convert them into inorganic compounds which contain nitrogen. So the ammonification really is part of mineralization. So that they have it as an extra step here. It's really part of that, so that's why I said there's 5 steps, but that's okay. I don't think we need to get hung up on the number of steps, just, you know, it's not easy to just straight up learn this right from off the bat here, but to try and remember, okay, what's the process? First it's the gas, then the bacteria put it in a usable form, then the plants assimilate that, they use it, and then after the plants die, mineralization happens. After that happens, then bacteria can start to break it down and make more of these same ions, NH4 plus, which will then get converted into NO2 minus and NO3 minus. So the atmospheric nitrogen can be essentially converted right into those ions, and then when the plant dies, the same thing happens. Right, there's your cycle. So these are actually pretty good. The way that they're writing, this is just what I have. And then the denitrification is the conversion of NO3 minus by specialized bacteria, nitrous oxide, N2O, and eventually nitrogen gas, which is emitted. So that's literally the end of the cycle, and then it goes again. So that's when the nitrogen's put back into the atmosphere, when you have specialized bacteria, again, anaerobic conditions. There's no oxygen involved with this. It's not the oxygen cycle, it's nitrogen. So these bacteria, it just kind of blows my mind. It's pretty cool. I mean, it's insane. The more you learn about this stuff and the more you learn in this class, I hope you get as excited as me. It's like everything is here for a reason. Every little thing, even a little bacteria and fungi, or fungi, some people say. And without them, this wouldn't happen and life couldn't exist. So, you know, we don't think about cyanobacteria on a daily basis, but they're like probably more important than me. Definitely, not probably, definitely are. So it's like crazy things that you learn. And then leaching, I actually don't really have, I mean, I have it here in my notes, but that's just another small process here. Dissolved molecules get into groundwater through leaching. So nitrogen ions that are in the water that the plants are absorbing can get into groundwater through leaching. I wanted to get phosphorus done. You know what? Phosphorus might be a little homework for you guys. Learn phosphorus. So that's leaching. We're good. There's a lot to write there. I know I'm talking. No, okay. Yeah. So, if anything, I think the way I'm kind of teaching the class, and I am grateful for these PowerPoints. It's just easier. I don't have to write as much like I do in other classes. But in college, you know, get ready for that. They just talk and go, and they're not waiting for anybody. So sometimes you have to listen, write, make sense of things all at the same time. So it's good practice for you. I wish we had twice the amount of time to do that. I wish we had double period every day. Does that sound familiar to some of you?
Yes.
I wish we had 3 periods. That actually, you know, I don't like block scheduling, but it would be, I think it could be beneficial for AP classes. Regular classes, I don't really need Regents kids for like an hour and a half. And that's nothing to do with them. It's not the students, just, unless we could do a lab, I don't know, it could be beneficial. All right, anyways, so there's leaching, and then the next slide is just the picture of the nitrogen cycle. And before we get to that picture, what's the biggest human impact? Huge, big problem. Hey, Caleb. I'm recording, so that's good. Let's see, who do I want to put on the spot? She knows it's coming. Kaylinol. Or you can phone a friend. It's not an easy question, so don't feel bad. Do you happen to have an idea? What is something humans are putting into the environment that is disrupting this cycle? If you don't know, it's okay. There's a lot of people sitting here that don't know. Anybody know? How do you make them grow? Fertilizer. Write that down. Circle it, underline it, bold, stars, smiley faces, whatever is going to help you remember that. It is an enormous problem. That's where algal, I have trouble saying that word, blooms come from. Because when it rains and runoff gets into the water, there's way too much nitrogen and phosphorus, and the plants are just like, hey, look at all this nutrients. We're just going to grow out of control, especially algae. Fertilizer, and that can come from manure. It can come from synthetic fertilizers. So it's disrupted the end nitrogen balance. Some species have a low tolerance. The next unit, a lot of what we learned in this unit applies to the next unit, so we'll go faster. But some molecules, organisms are low nitrogen tolerant. Meaning, when they experience this fertilizer from runoff, they die. It's too much nitrogen. So it's not just growing too many plants, sometimes some die. So I am basically out of time. I am going to give you bookwork. The bookwork is going to ask phosphorus cycle questions. You're going to have to use your book. I will go through phosphorus cycle tomorrow. I'm not going to just ever make you learn something completely on your own, but I will send that out later. You guys can have a good rest of your day.